Hi, my name is Brandon Lee, and I'm a student at John L. Miller Great Neck North High School. This is my project called Analysis of Geomagnetic Storm Effects on Satellite Orbital Decay. I completed this research at the Cooper Union Summer STEM program, and today I'll talk about how I developed a computational model of low Earth orbit satellites to study how geomagnetic storms and other factors influence satellite lifetimes. Many modern satellites, such as SpaceX's Starlink satellites, operate at low Earth orbit, or LEO, which exists between 160 and 2,000 kilometers above Earth's surface. At these heights, despite the very thin atmosphere, satellites experience orbital decay, where atmospheric drag causes them to slowly lose orbital energy and altitude, eventually leading to atmospheric re-entry. Atmospheric drag is dependent on the atmospheric density, which varies based on certain factors. For instance, solar activity and geomagnetic storms cause atmospheric heating and an increase in density, leading to more drag and faster decay. As shown in the diagram to the right, Starlink satellite reentries have seen a dramatic increase as solar activity became more intense. This is a significant economic and environmental issue. Thus, my project aims to articulate how exactly do geomagnetic storms and solar activity affect the expected lifespan of satellites in low Earth orbit. My project has two main objectives. My first objective is to develop a physics-based simulation of low Earth orbit orbital decay, which accounts for more realistic effects such as atmospheric drag, long-term solar fluctuations, and random geomagnetic storms, all of which periodically boost atmospheric density. My second objective is to use that model to identify which parameters are the most important for satellite lifetimes. By understanding how things like initial altitude and the satellite's mass-to-area ratio influence decay, we can significantly improve satellite designs. Here's a quick overview of my model. I simulated a single low Earth orbit satellite and processed it through a series of time steps. I characterized the satellite using a few parameters like initial altitude, initial velocity, mass, cross-sectional area, and the satellite's drag coefficient. I assumed that the satellite was in a circular orbit, and I set the initial velocity as the standard expression of the square root of gm over r plus ho, where g is the gravitational constant, m is Earth's mass, and r is Earth's radius. To compute the drag on the satellite accurately, I created a model of the atmosphere and how it changes over time. I started with the baseline atmospheric density, which decreases as altitude increases and is given by the formula rho of h is equal to rho o times e to the negative h over h, where rho o is the reference density and capital H is the scale height. I also included solar activity, which I approximated as a sinusoidal 11-year cycle, represented by the formula f solar of t is equal to 1 plus k sine of 2 pi t over t. This makes the atmospheric density higher at the solar maximum and lower at the solar minimum. Moreover, I used a stochastic storm generator that creates storms at random start times, intensities, and durations. During these storms, the atmospheric density is multiplied by a scaling factor between 1.5 and 5, and the durations range from 2 to 48 hours, and there is a roughly 5-day gaps between storms. Finally, I combine all of this into a final density, which is part of what I need to calculate the orbital decay on the satellite. Now, let's explore how the orbit is actually updated. So the simulation is run across time steps of 300 seconds, and at each time step, I use the atmospheric density to calculate the drag force using this equation, where v is the orbital speed and a is the cross-sectional area. Then, dividing by the satellite's mass gives us the acceleration caused by drag. Finally, I use an energy-based approach which relates the rate of change of the orbital radius to the drag deceleration. Using this, I can calculate the rate of orbital decay, which is used to update the radius and the velocity. This process is repeated until h falls below 100 kilometers, which is when I deem that the satellite is re-entering the atmosphere. The satellite's total lifetime is then recorded as a function of those conditions. Using these, I ran the simulation across many sets of parameters. Moving on to my results, the first key result shows how altitude changes over time in a single sample simulation. The blue curve shows the altitude of the satellite, starting from 350 kilometers and an initial velocity of 7,700 meters per second. The shaded red regions are periods when geomagnetic storms are active in the model. By observing the graph, we can see that geomagnetic storms create sharp drops in altitude because the atmospheric density is heightened and drag is temporarily much higher. Additionally, near the end of the satellite's life, the curve becomes much more steep due to the exponential growth in decay. This behavior gives us a crucial insight. A small amount of propellant can be used to delay reentry in that critical low-altitude region to disproportionately extend the satellite's lifetime. The second result looks at a broader parameter scan, in which the simulation is iteratively run over many different variables. The 3D surface shows how the satellite's lifetime, which is represented by the y-axis, depends on the initial altitude and the average storm interval. As you might expect, the higher initial altitudes lead to longer lifetimes, since the satellite has more distance to fall and it starts in a thinner part of the atmosphere. Second, if the storms are less frequent, the lifetime also increases because there are fewer spikes in density. Overall, the steepness of the surface exemplifies how a small decrease in altitude can cause a large drop in lifetime. My third result focuses on satellite design, specifically the mass-to-area ratio, denoted by psi. Psi is defined as the mass divided by the cross-sectional area and is in kilograms per square meter. As psi gets bigger, it means that the satellite is more dense and compact. This is important since that means that the satellite has more inertia to drag. The plot shows the satellite lifetime as a function of psi when all the other parameters are held constant. It's clear that there's nearly a linear relationship between psi and the satellite's lifetime. Thus, when the initial altitude is constant due to mission requirements, psi becomes the main design lever that controls lifespan. A high psi satellite has better resistance against orbital decay than a light, low psi satellite. To summarize the main takeaways, geomagnetic storms create short bursts of heightened drag, which in turn lead to sharp accelerations in orbital decay. Moreover, because of the atmosphere's exponential nature, orbital decay is also nonlinear, and once a certain threshold altitude is passed, reentry occurs very quickly. This means that using propellant before these drops is much more efficient. Third, a higher initial altitude and lower storm frequency correspond with longer lifetimes, but when these are constant, the mass-to-area ratio is the most important parameter, since increasing psi dramatically extends lifetime. Of course, my model also has several limitations which should be acknowledged. My model makes many assumptions and simplifications which don't model realistic scenarios to the best extent. For instance, the solar cycle is simplified to a single sinusoid, which doesn't account for more detailed variations. I also use idealized intensities, durations, and spacings, which could be calibrated with real satellite data to give a better insight into the orbital decay of these satellites. The drag formulas I used for atmospheric density are also simplified, and my satellite doesn't account for the actual geometries or shape of the satellite accurately. For future work, a good idea would be to calibrate the model with actual measurements, which would make the model more accurate. Calculations could also be more precise, and finally, it would be helpful to explore other satellite geometries instead of just assuming a simple shape. Finally, this research was done at the Cooper Union Summer STEM program. I'd also like to thank my mentor, Abdullah Ali, for his guidance and feedback while completing this project, and the Cooper Union Summer STEM program for providing the environment and support that I needed. Thank you for listening, and now I'll open up for any questions.